Good morning, everyone. Yeah. Uh, hope everyone's had some coffee. Otherwise, I will put you to sleep. My talk today is called Multichannel Madness. And that image we have there, it's got a spelling mistake, yes. That is generated by AI, where I told them to give me a PPT presentation. So it's basically, it's madness. It's multi-channel madness. So let's get into it. So often when building medium to large size systems, we need to build a configuration page to enable the user to configure multiple channels individually or as a group. Countless hours can be spent painstakingly navigating through configuration files and building the appropriate UI, LabVIEW appropriate UI for this purpose. Now, LabVIEW's configuration editor framework is here to change that. Well, it's been around since 2011, but there's little adoption. It is a powerful tool designed to simplify the process of creating and managing configuration settings for applications, particularly those involving multi-channel or complex configurations or multi-device. So the way I look at it is I start with multi-channel, then I go to multi-device, and from multi-device, you can have multiple instances of the same device or multiple devices, etc. Yep. Wait, okay. Slide is not changing. Next. Okay. Yeah. So a brief introduction about myself. My name is Vishal, and I've been working with LabVIEW for the past almost 2+ years. The first time I was introduced to LabVIEW was in my final year thesis project, where I've just given this bunch of motion stages, and I was trying to align optical fibers with them. I didn't. If I look back at my code, it's just spaghetti code, but yeah, I've gotten better. I like to think that. I was formally introduced to LabVIEW through my first job, where I learned a lot. And right now I'm working with a semiconductor company in Brisbane. All right, so now let's get into the meat of it, if you will. So how many of us have heard of the configuration editor framework before? 1, 2. Okay, yeah. Yeah, so that's probably true. Like it's not that well known. It's not got many users, and even though it's been there for a long time, I think the primary reason for that is there's not much resources to on how to use it and how to extend it, and this presentation is an effort to do that. So the configuration editor framework can be downloaded from the IPM. It's free. It comes shipped with 2 templates. We'll look at them later. Now on my screen, you can see the very familiar NI Max. This is a configuration editor, wherein we have a subpanel, which is the red box there, and then you have a tree structure, which is the green box there. Based on the selections the user makes on the tree, a different subpanel would be inserted into the subpanel node here, and we want to build something. We want to build something like that. The configuration editor then stores the user inputs in local memory called a repository, and ever so often it would write to this repository the changes that have been made, and also this write operation can be automatic. It can be user-defined, where the user selects save, and then you'd go ahead and save the configuration. And then, of course, this can be reloaded at a later point. Now, let's look at some of the features of the tree structure and kind of get an understanding of what we want to achieve with a configuration editor. The first thing we can notice in a tree structure is that it is hierarchical. Now, in this tree structure I have here, we can see there are 3 levels of hierarchy, where you have the My System, which is the top level. Then you have the devices and interfaces, software, remote systems, which is the level 2. And then within software, we have all the softwares level 3. So we want to create a tree structure which is hierarchical, and yeah, so that's one of the features, and that's taken just from NIMAX again. Now, if yeah, got to go the other way. Yeah, so let's run this. So here you can see very simply, you can make out this area is the sub panel, while here we have the tree structure, and we've got a device already. So it comes shipped like I have not made any changes, no edits to this. So you get a serial there. Then we can go ahead and right click, and we get a function add, and you can add a group. So probably a group of channels, I would assume. And then on group, you can go ahead and right click, and then you get add, duplicate, and remove. Now you see you don't get those options with the serial now. It might seem very trivial when I'm saying these things, but a lot of these things are controlled by functions which are customizable. And when we look further into the project structure, we'll understand that in more detail. Now I can add a current channel, I can add a voltage channel, and they've got their own settings which can be set up. I can also duplicate this group, or I can come here and remove this group. There's also file functions where you can open a new one, open, save as, exit, the regular stuff. But right now, the one problem I see with this is it's limited to a serial device. Maybe you could change the class name to a different device, but to extend this to multi-device, that's what I want to focus on. And that's where I spend most of my time working and trying to figure it out. And I thought this would be really useful. So let's exit that once. Yeah, I'm not going to save it. The default setting right now, it just saves it as a binary.xml file. So yeah, we've seen the tree structures. Now let's look at the project folder. So this is a snapshot of the project, and if we look at the different nodes that we added onto the tree structure, let me just mention again. So each element in the tree structure, we'll call it a node, and each node, as we can see, is has a corresponding class that has to be created for it. So the serial has its class. You've got a group class, a channel class, a current class, a voltage class. And so if you want to add more nodes, you'd have to create more classes in this fashion. Here I come to my the second tool that I use with the CEF is the GDS, or the group development, which won me the bottle yesterday. Thanks a lot for that. I use GDS to clone my classes. It's really helpful there, where I don't have to create all the functions again and make sure the names are correct, etc. I can just right click, group, clone, and takes care of me of that stuff for me. So yeah, and also each of these classes are DVR reference classes. This project was the first time I was working with DVR reference classes, and I was quite overwhelmed by the concept of it and how it all works. But once I've used it, I think it's quite easy to wrap your head around it, and it's not as hard as it seems. So yeah, now let's quickly have a look at the architecture of the configuration editor framework. Now this image is taken directly from the NI CEF documentation page. The link is given below. The primary block diagram we see here is the repository. Now this repository is the in-memory location where the configuration is stored. The repo is a class. Just like each node on our tree is a class, the repo is a class. We have multiple nodes where you saw group, channel, serial, etc. But you have just one. Each project would have only one repo class. So this the configuration from the repository is read and written by various entities. First of which is our tree view. Then we have the file which reads and writes to this. Now this file could be a binary.ini, XML, JSON, etc. And the last block diagram we have there is called a custom view. Now, custom view represents a view other than the tree view, which can be used to navigate the configuration or make changes to the configuration. The shipped example comes with a custom view called the multiple channel editor. Although in my experience, when I implemented it for an application, for a custom application, I find that it's the moment you have multiple devices and multiple channels, the custom view stuff doesn't. It's very difficult to create custom views other than the tree view. So I feel the tree view is the best view to navigate navigate the configuration file. Now. So as I said, each CEF project should have one child of the repo class and several children of the node class. Now, each of the nodes that we have there, they inherit from a base class called the node class. This node class will be somewhere in your VI-lib part of your dependencies. I've made one or two small tweaks to it, which I will show you. But other than that, you wouldn't need to touch the base class, and you would just override methods of the base node class for each of the nodes that you're creating. So here I have shown some of the common methods that are implemented for a node. So duplicate is this method chooses what happens when you right click and select duplicate. So in the previous case, in the example that I showed, it adds the suffix copy. Edit options, it chooses allowable child nodes, which is basically when you hover over when you right click a tree node and you have the add function, which then shows you the allowable nodes which can be added under a certain tree node. So that the names of those nodes and if a node is removable, movable, or copied is in the edit options. And if you remember the Serial node, you couldn't move it, you couldn't remove it, or you couldn't copy it. So that means you're in a way limiting the devices over there. And for each node that's customizable, that happens through the edit options. Then you have the from repo. This function reads data from the repository. Now, if you were just using the shipped example and doing just one device, you wouldn't have to touch this. But the moment you go onto multiple devices, we need to customize this for our nodes. Then you have the group UI, which is the user interface you see, which is the sub panel, which is popped into each time a new node is clicked. You have the initialize VI, which gives the initial settings when you add a node, some base settings, if you will. And then you have the to repo, which would pass the data for the repository. Next, we look at some of the methods and functions of the base repo or the only repo. I've called it the base repo here, but this is the only repo class that you would have in your CEF project. I've only given functions of some of them because the others, honestly, I haven't touched them. You wouldn't need to either, I would assume. So custom view, it defines the custom views other than the trees. If you have a question, you can just always raise your hand. We have a Q&A, but yeah. Then we have the OpenVI, which reads the configuration file. I have edited this method in my example that I have here because this works. The shipped example has a binary file that it writes to, but I have modified it to work with JSONs. And then you have the that should have gone to save. It's gone to write tree, that arrow. Yeah. So that saves or writes back the configuration. In my case, it builds my JSON each time, but it depends. It depends on your custom implementation. Now, if you want to know more about some of these node level functions, please refer to the CEF documentation on this. And plus, there's also a very helpful video by Tom, and that's his YouTube channel, Tom's LabVIEW Adventure. Yeah, he goes further into detail of all of these functions and how to edit some of them. I will be doing some of that now, but again, I'm focused more towards how to extend and add multiple devices. Where if you want to customize some of the things like change, so I don't know if you noticed, but each node has its own glyph, which is at the start of the node. There's a small image which you can add. Like if you have a sine waveform, you could have a sine, or a PWM, you could have a square wave and things like that. So he goes more in detail of that. So yeah, that's and this is actually an embedded link. So once we distribute these PDFs, these PPTs, you can directly access the video there. So the first thing when we want to extend this hierarchy, when we want to extend the CEF, is we need to define the hierarchy of our nodes, as each node needs to know which node/nodes are its children. And in the Cerio example, we see the hierarchy of nodes that I've drawn here. It's just this part, not the signal generator stuff. So it starts with the base repo. You go to the Cerio class, and then you have the group, and then you have two channels, current and voltage. Current and voltage, they both inherit from the channel class. So they don't have independent data even. Their data is shared. I mean, it's the common channel class data. They just have their own implementations of initialize and I think one more VI. But yeah, so it's the flow of data is quite linear. But what we want to do is I've taken an example where I'm just adding a signal generator. I think the one I use in my example is an Agilent function generator where you can generate a multitude of signals, but I've taken only 3 over here: a sine, a frequency sweep, and a PWM. Now, in this in the Cerio class, the lowest level of hierarchy here, channel, also the data is shared between current and voltage, but sine, F sweep, and PWM will have independent data. And I want to show how to implement that level, how to add nodes which don't have, which have like dissimilar data. And also the group class will be shared amongst both the Cerio and the signal generator top level classes. Yes. Now if you would look into the edit options VI, as I said, that's where you add the shortcut menu options that can be initialized. Now, if I want to reuse the group class, if I actually go back, if I want to reuse my group class, when I right click on a group node, if it inherits from Cerio class, it would show current and voltage. But if it inherits from signal generator class, it should allow me to add a sine, F sweep, and PWM. To do that, what I need is a case structure in my edit options VI that would, based on the group type, define the shortcut subnode menu names or shortcut menu names. And so to do this, I've created a group type. And this group type is initialized in my initialize VI. So the So the parameter the parameter input was already there in the initialize VI, but it wasn't used. So I'm using that to initialize my group type. And the initialize function, which is this one here, if you could see the node initialize. So these are dynamic dispatch functions. So each node would have its own initialize VI. And this input over here is the parameter input. And I have given it the node class, the name of the node class in the add node VI. So now each time a new node is initialized, it would also get the name of the node it's inheriting from. And that's how our group node will then be able to decide which shortcut menu it should display. So that's one of the quick changes that we can do to move to a multi-device configuration. Next, I want to look at the functions which write to the repository and read from the repository. So in our repository class, we have open.vi function, which reads currently from a binary file and converts it to a LabVIEW data type, like so. Next, yeah. Which this is the native. This is the example implementation we have, where we opening a file, it's a binary file, we flatten it and then convert it straight up to a channel data type into an array of clusters. But we wouldn't be able to do this if we had, if our channels were not of the same type. Then you couldn't convert it into an array. Yes, you could use a variant, but then you would have to again convert those variants into the correct data types when you actually initialize those classes, because this one's not initializing, it's just opening the file and saving it to the repository. So the way I've fixed, or I've tried to address this issue is that I don't use binary files. I use any text-based files like JSON or XML. And then when I read my configuration files, I don't convert it. I don't convert it to some sort of LabVIEW data type in the sense. They're still string data types, but I keep them as JSON strings or XML strings. If that makes sense. I don't convert it to a particular LabVIEW data type. Yeah. So yeah, and after we read our data from the file, it is then passed on to the various from repo implementations of our nodes. So yeah, this is the implementation I've done, where I'm just reading my JSON file, and it's got 3 objects, and those 3 objects I'm writing them to a JSON cluster here, and this JSON cluster can then be called in by my from repo methods, and we will see how in a minute. Oh, I might do that. Okay. Yeah. So yeah, next I want to talk about the from repo and to repo functions and how they're implemented. It took me quite some time to wrap my head around this, but hopefully I can tell you how it works in the next 10 minutes. So we're looking at from repo first. From repo, as I said, is a dynamic dispatch function and has a parent class implementation and individual child class implementations. When we start this function after reading after having the open function from the base repo, we're going to call the base class or the top level class that you have, or your top level node. This is the top level node for me, which is my base repo implementation. So here I take the JSON cluster, and then deciding which classes I need to initialize after this base node is created. And I pass the names of those classes as an array. I also pass in some tags, which in this case is the individual JSON strings for the CDO and the signal generator objects. The classes also, so the class also initializes its own data. So the base class's own data is just the version number, so it would initialize its own data. And it would also decide or tell my parent class implementation. And by the way, this is the call parent class implementation. Do I have a pointer for that? Yeah, I have a pointer for that. So yeah, that's the call parent class implementation. And we'll look at that in a second, but we need to know that the data we need when we're opening up a new configuration, each of your node classes will need to tell the parent class implementation which node to initialize next. And that's what we're doing here in this. You need to pass that data as an array as a part of this cluster. And there's also some tags which you can pass, which can be used later on, although that is optional. So this is my node base class implementation or parent class implementation. There's no changes made to this. This is how it comes shipped in. As we see, we take our classes, pass it in a for loop, and here, this, do I have some more? Oh, no, let me go back. I had some pointers there. Yeah, so where was I? Yeah, we go into the for loop, and based on each of the class, it's going to search for that class over here. Yeah, it's going to search for the class path over here, and then it initializes that class. And we typecast it back to a node base class. We tell the class who its parent was, and then we go into the from repo implementation of that class. So it's kind of, it basically goes into a loop. So the way this works is, we have the for loop that iterates through the classes, creating their DVRs and calling their from repo method. So this is kind of a recursive process where it's important. And it's important to, this kind of recursion, it's kind of difficult to wrap your head around, and I think it's important to understand this. Otherwise, you wouldn't be able to implement it successfully. So each from repo function initializes the data it needs for its class and decides which classes to create after that, and then passes this data on to the parent class or the node class implementation, which is here. Now, this would then create that class and its DVR and call the new classes from repo function. And this goes on until the last class. And in the last class, you would just pass an empty string of classes, an empty array to the classes, and then it would stop. The toRepo function is implemented in the same way. So in the toRepo, you're building your JSON and writing back to the file, except that you don't need to put in the logic to decide which class to go to next, because it already knows it. The way it knows it is it links those classes here in this link node vi. But again, the reason I don't have many pointers here is because I don't really touch this, because it's and you don't have to. Now here is the toRepo parent class implementation. Here you can see it's much simpler, where I'm just I use my toRepo methods to iteratively. I'm using my toRepo methods to iteratively build my configuration JSON, wherein each node class adds its bit to the larger configuration JSON, and it follows the same logic as a from repo, where you would always call the parent implementation after the node classes implementation, and that would then call again the new from repo method, and this it goes on in a recursive loop. Yeah, and that's a bit of the theory behind it. But now I want to show you my implementation of what I have done, kind of a demo. If you can see here, sorry, I cannot see. Yeah, this is a project that I created. Other than the CDO, I've created classes for each of the nodes that I need. I need a signal generator node. I need an fsweep, PWM sign. If we quickly go ahead and look at the data within these, as I said, current and voltage share. They don't have their own data. They share the data or the only data they have is their parent class or the channel class data. But that's not the case with PWM, fsweep, and sign, where they have their own. What's opening on this page? Where they have their own data, and it's quite dissimilar as well. So we can refresh rate is not good. I don't know if you could see that the refresh rate is not great, but let me just go ahead and run the main for you once. Have it? Yeah. So here my top level class is just my base class, where I have a version number, and I can add a serial now, and I can add a signal generator. Under the serial, serial is basically the same. I add a group, current, voltage, signal generator. Again, I can add a group, but now because it's shared, we see that over here, instead of current and voltage, it would show f sign, fsweep, PWM. So I can add a sign, fsweep, and a PWM. If we look at our current channel data and voltage channel data, we see it's the same. It's the same data type that's shared across, but that's not the case with my sign, fsweep, and PWM. And that's usually how configurations are. So you wouldn't have similar kind of data where you can put it all in a parent class. So, and then we still have our other functions where we can duplicate and okay, it is weird. My remove function is not there. Must have disabled it. Doesn't matter. But yeah, and now let's go ahead and save this. Where will the pop-up screen come up? So it gives me a pop-up screen. I'm just going to my editing. Just going to save it on desktop for now. Let's call it config2. The JSON file. Okay. So that's saved my configuration. Let me go ahead and exit it. Let's run it again and try opening the one we just saved. Is config2. Okay, yeah, and we see we get our configuration back. So that check is important. So now we know that our from repo to repo functions are working well and doing what they're supposed to do. So yeah, that's how to do an implementation of the configuration editor framework for multiple devices. And if you've not, if still some things are murky or not clear in your head, I would advise you to watch Tom McQuillan's video and then rewatch this. So because that gives a much better introduction to the configuration editor framework, whereas I was focusing more on how to extend it. So that's my time. Thank you so much.